All right. So I think these are the axioms that George puts in his book, and they're all reasonable statements. Um, and he emphasizes you don't need to have intuition, right? He says adding intuition throws you off, and you should be able to just mechanically follow the rules and get a proof, right? So you can prove theorems with as few assumptions as possible, talking about, right? You want to talk a few assumptions about the objects so you can find a wide range. This, you've seen that slide already. So my dear friend Tony, she teaches this proof system, which, right? It's not too hard to prove things from it, but again, it doesn't give me much intuition. And this is the proof system that Gödel does incompleteness theorem on. And so one object, these people want to have the smallest proof system sort of possible, right? To have as few rules. But I kind of been going the other direction, giving you lots of rules, right? The purple table gives you a lot more rules so that you can make it easier to prove things. All right, so now let's go into, so one type of proof system, which the one we gave by Tony isn't this, is a Hilbert, called it a Hilbert proof style of proof, in which you have these lines of proofs. And what do you need? Well, you need each line is either going to be one of your axioms, all right? And we have two types of axioms. We have logical things that you've already have proven to be true in your logic, like modus ponens, right? Or contrapositive, right? These are all things that are already known to be true in every universe. And you can add other axioms that define your objects. Like if you want to do logic about the integers, then you can say, well, one thing about the integers is a plus b equals b plus a, right? And you can add axioms like that. And then you can also add lines that follow from your rules, right? You have a rule that says if these strings are in your proof system, right, then you can add this other string to your proof system, right? That's basically what the purple table does, right? It says if you have this and this, then you can put in this, right? And then the question, whether you want to have meaning there or not, right? Oh, here I'm just sort of saying, adding meaning here, saying, well, this means, right? This is a right. So one thing that my proof this I guess is starting on what I was adding to it is I wanted every line of the proof to have an understandable meaning, right? So here, if you have a free variable, then that means for all, and if you have an exists variable, then that means exists, and this here means there exists one object that works for every x, right? In fact, this means the statement alpha itself is a free variable, right? Well, if we put in the function here, right? Then it's saying that the y can depend on the x, right? So this will mean now it's kind of switches these, right? This says there exists one function that works for every x. This says for every x there exists one object. Yeah. Well, that's a good question. If everybody I'll tell you what's going to be on the exam is whatever we cover here, right? If we say, hey, what do you guys want to cover? And people don't want to cover a lot of these formal proofs, then they won't be on the exam, right? I mean, the joy here is the exam's not made up yet, and we'll decide together what we want to cover. If you get me to teach it, then it'll be on the exam. And I would, of course, my ego wants you to like the way I do it, but you can decide too. Hey, you like the formal proof system, and right. So here's some extra meaning, right? If you assume this, right? If you're doing deduction, right? You assume alpha, and you later then prove something else with that assumption. Then the underlying assumption is that when you write this, right, this is an indent, right? You assume alpha and then you indent, right? As long as you're indenting, there's the underlying assumption that you've assumed alpha, right? If you people don't understand something, holler, right? So this is how I'm adding meaning to every line, right? If it's indented, then we're assuming that your assumptions are true, right? You say, hey, I assume alpha, and then you indent, right? Doing a deduction, right? Then you have all these assumptions. And I don't think that this detail really matters, but we have these slightly different notations of free variables. But here's all your. I made it a vector because you have lots of free variables, right? You assume all your free variables. So going the other direction, right? Here we want to say that it's true in every model, right? In any model, right, there exists these objects, right? Once you tell me the model, then I can know what my objects are that I'm assuming exist. And these could be fixed objects, or these could be functions of the free variables. And then you have, well, it has to work for all free variables, right? That under the assumptions you get the statement's true. Right? So this is just the underlying meaning with, so that why I like the meaning is so that when I go through a proof, I do two things. One, I check, am I mechanically following the rules? And then I also in my brain says, yeah, and do I believe that the new statement I write down is valid, right? So you intuitively, right? So you do both, and and I think it's useful to do both. All right. Right. So again, yeah. No, because we're going to do it again right now. That was quick. We're going to do it slower. All right. So what kind of rules do we want, right? I think these are all good rules. I hope you've appreciated that these are helpful in our world. And do you need them all in your proof system? No, you could have just a few of them that from which you prove the others, right? And then, right, we have to bring in, what do we have to bring in? We have to bring in the idea of a quantifier. We have to bring in the idea of having lemmas and substitution. And probably we won't, this stuff is all, I think, is pretty natural, so we might not get to it. I stuck it into I made these slides to cover it, and then, well, we only have so much time, right? And how does this deduction, right? As soon as you have for alls and exists in deduction, that things can go wrong. and so it's important to look at the nuances of what can go wrong. Right? So here what can go wrong is that if you assume this and you prove this and you conclude this, right? Now you have to be a little careful about for which objects, right? Where do we put the for all? So it's the for all on the outside or in the inside, right? So that becomes nuanced. Oh yeah. So yeah. Yeah. So I guess so. So one of the first things I was trying to prove using George's following his proofs was that you could prove things that weren't true. And he said, well, you're supposed to, you have to say, when can I add the for all and the exists? Or, and this says you can't add the for all if it's part of your assumptions up here. And so instead of going back and having to see, oh, are my variables in my assumptions up here? I recommend marking those variables so that you can't do a for all on them. I treat them pretty much the same as the exists guys. Yeah, the arrow one and the exists guy are pretty much the same. I just put it here because it's sort of different applications. Right here you can say, well, I'm assuming this. Well, are you assuming it for specific values, or are you assuming it for free values? Right? It's nuanced, and we can give some examples where if you do it wrong, you get things that aren't true. Yeah, so the thing here is what we want. If we assume this and we prove this, then we want to conclude that no matter which object we had up here, if you assume alpha is true for that object, then beta is true for that object, right? And what you don't want to get is that, do I have it here? Oh, I mean, what we're avoiding proving is that for all x, alpha of x, right, gives me for all x, beta of x, right? It's a different statement. So you have to be careful there. All right, so here's the rules that I told you already. We can prove soundness. What does that mean? We can prove that if you follow these rules, then your statements are going to be true, right?